Last time we finished the proof of the non-vanishing theorem, and so in the process that also finished the proof of base point freeness, since we proved base point free assuming non-vanishing. Today we want to do the rationality theorem, but I wanted to make an aside first on the abundance conjecture, because now that we have the base point free theorem, we get as a nice corollary a case of the abundance conjecture, which we actually already used in the case of surfaces. So let me say something about that. Okay, so the abundance conjecture is the following. So if x comma delta is a projective KLT pair, actually in full generality, let's say it's a projective log canonical pair. Well, we want all the theorems for log canonical pairs, and the proofs end up being easier for KLT pairs, and assume that delta is a boundary, i.e. delta is effective. Then one, we have finite generation of the log canonical ring. Okay, and here I have to be a little careful because we want to write M delta, because we want to just say it's the ring of sections of multiples of kx plus delta, but kx plus delta is not Cartier, it's just Q Cartier. So we have to round down here. And now you can convince yourself that if you round down and take sections, then you multiply sections, then they really land in H0 of the round down. So that this thing is really a ring. So first part of the conjecture is that this is a finitely generated ring. And the second part is that if kx plus delta is nef, i.e. we've run the minimal model program and contracted all kx plus delta negative curves, which we'll see how to do in a second. By in a second, I mean in a few classes. Then kx plus delta is semi-ample. Okay, so that's the abundance conjecture. In this generality, it's still completely open. But based on the base point free theorem, we get one case of the abundance conjecture, which is essentially the case of pairs of log general type. So any questions on the statement before I move it? So corollary of base point freeness, suppose x comma delta is a projective KLT pair. And suppose kx plus delta is big enough. And so I'll just make a definition here. If we have kx plus delta big, we say that the pair is of log general type. Where we already talked about earlier in the class, general type is when kx is big. So in the pairs case, when kx plus delta is big, we call it log general type. So suppose we're in the log general type case, but also that kx plus delta is nef. So we have a minimal model. Then the abundance conjecture holds. And again, we use this already in the case of surfaces, where we said that if we're in the case of general type surfaces when we were doing our classification, then we said that by some theorems that we'll prove later, kx is actually that if the surface is minimal, i.e. kx is big enough, then kx is actually semi-ample, and so it has a canonical model. Okay, but now we have it in general. So pick some m greater than 0, actually m greater than 1, such that m kx plus delta is Cartier. And let's just call this d. Then we know that d minus kx plus delta, because we picked m greater than 1, then this is big enough. And d is Cartier because it's a multiple of a big enough. Sorry, d is Neff because it's a multiple of a big enough divisor. So d is not just Cartier, but it's also Neff. And so by the base point freeness theorem, d is semi-ample. But since d is a multiple of kx plus delta, then in fact kx plus delta is semi-ample. So we can just write it as saying there exists a b so that b kx plus delta is base point free. Okay, so that's the second part of the abundance conjecture. That kx plus delta is semi-ample, but now we still need to use that to show finite generation. So once we have that b times kx plus delta is base point free, let's just take its linear series. So we have some f from x to z, some projective morphism. Let's say we've normalized the target, so z is normal, and then we know that b kx plus delta is the pullback of some ample class on H. Okay. But now let's define some sheaves on Z. The push forwards of the things whose global sections we care about. So these sheaves are the form mkx plus the round down of m delta. Now, by the projection formula, if we take GM tensor OZ of H, then this is the same. Well, H pulls back to be B times Kx plus delta. So if we tensor it with these push forwards of M times Kx plus delta, we should just get GM plus B by the projection formula. Okay, but now just putting it all together, we have that the canonical ring of X comma delta is the direct sum of the sections on Z of these GMs. But when M is a multiple of B, then we just have maybe I'll say it a little differently. If we look at this, the ring of sections of H on Z, this acts on R kx plus delta, but by this equality over here, it actually has to be finally generated as a module. So this equality tells us that R kx plus delta is a finitely generated module over R of H, but R of H is finitely generated because H is ample. Okay. So that gives us finite generation. And so essentially this argument really tells you that when you have a base point free divisor or a semi-ample divisor, then its ring of sections is actually finitely generated. So that was just an aside. Now that we have base point freeness, we get that. Now I want to prove the rationality theorem. So we're building our way to proving the cone theorem. The rationality theorem, the key idea is still to use this base point free method that we've used for the last two theorems. But this one maybe is the most involved of all of them. So let me recall the statement. Let x comma delta be a projective KLT pair with delta effective. And suppose that kx plus delta is not an f. And let's define a to our fixed sum a such that a times kx plus delta is Cartier. And let h be a big enough divisor. We can say Cartier divisor, but the statement is invariant under scaling, so it doesn't matter so much. If we say Cartier, Q Cartier, then we'll define this NEF threshold to be the maximum or the supremum over T and R such that H plus T Kx plus delta is NEF. So Kx plus delta is not NEF, so if we keep adding some large multiple of Kx plus delta, we'll eventually get some negative self-intersection. So sorry, no, intersection with the curve. And so eventually this will cease to be NEF. So we'll take R to be this kind of threshold where it ceases to be NEF. Then R is U over V. In particular, it's a rational number with a bounded denominator. So I want to say something about the rough idea. So let's say we pick some numbers Q and P, so that Q minus 1 over P is less than this threshold R, but Q over P is bigger than R. Then we can look at the divisors PH plus Q minus 1 KX. So here it's the same as looking at T below this threshold. So this is NEF, but in fact we can arrange it so this is even big enough because H is big enough. But on the other hand, if we add one more multiple of K, then we're above the threshold. So this is not, I mean, it's not NEF, but what we really care about is that since it's not NEF, it's in particular not semi-ample. But the point is that these two divisors differ by just one multiple of kx. So if we let this divisor be d, then the cohomology of kx plus d vanishes for I greater than 0 by kv vanishing. Also here I was writing it in the case where there's no boundary, so let me just add a boundary, because of course we have a delta floating around. Okay, let me make sure I put the delta there. Yeah. Okay, so we have these pairs Q and P where when we're right below our threshold, we have a big enough divisor. So when we go one more kx plus d, then we're no longer big enough, so we're no longer semi-ample, but we still have this vanishing of cohomology because of cohomology vanishing. And so this by itself doesn't tell us much, but what we're gonna show is that if R is not rational, then we're going to produce many such pairs with the extra property that this divisor that's above the Neff threshold is still effective. So we're going to produce a lot of pairs where even though it's not Neff, it's not semi-ample, it actually ends up being effective. But now once we have this effective divisor whose cohomology vanishes because it's of the shape of one of these adjoint divisors in Kalamata Vivek vanishing, where the other term is big and Neff. Let me now we're going to run the argument of like this base point free method, where we produce sections by induction by kind of resolving, perturbing the coefficients of this guy by adding some relatively amples and cutting out one smooth divisor with coefficient 1, so that when we restrict to that divisor, we have sections by our previous theorems, and then by the vanishing that we have for this p comma q, by this Kalamata Vivek vanishing, we can lift those sections, but then that will give us a contradiction because we have this effective divisor that's not semi-ample, but then by kind of perturbing things and restricting, we're going to get some sections that slice the base locus even smaller, and then some kind of Noetherian induction will tell us that we can't keep slicing the base locus smaller and smaller. Eventually, we'll get something semi-ample, and that'll be a contradiction. And the point is that we have to use, like, this only works because R is not rational, so we have this wiggle room to perturb things and not kind of mess up which side of the threshold we're on. So that's the very, very vague idea of what's going to happen. The proof itself is going to be very involved. It has 10 steps, but I wanted to at least get across this intuition that this is really what's going on, and the key point is this where this irrationality comes in is that you get a lot of these pairs with some special property. Okay, so let's begin. So first, just a reduction without loss of generality. We can assume that H is base point free. And the idea is just that if we define a new H prime by taking a large multiple of a divisor that satisfies the hypotheses of the base point free theorem, say CH plus D times A kx plus delta, where M is really large, even larger than C, which is much larger than D, which is greater than 0, then we have kx plus delta plus, or we have a multiple of kx plus delta plus C over DAH, where H is big enough. So this divisor here is semi-ample by the base point free theorem. And so some large enough multiple is base point free. But if we just if we just compare the Neff thresholds for these two, for H and H prime, well, there's going to be some numbers. Sorry, I don't want H here. If we look at H plus R kx plus delta, this is going to be Q equivalent, i.e. some up to some multiple equivalent to H prime plus some R prime kx plus delta for any R. Just because H prime is itself a multiple of a sum of kx plus deltas and h's. And so if you just solve, that tells you that R is R prime plus MdA over MC. So in particular, R prime is rational, implies that R is rational. But we also need this bound in the denominator. But if we look at this expression, if the denominator of R prime is V, then the denominator of R is going to be a divisor of MCV. But M and C are arbitrary. Here we said we could have taken M and C arbitrarily large. So that tells us that whatever the denominator of R is, it has to actually just divide the denominator of R prime, because this M and C we can make whatever we want. So just to get with the notation, let's say this was U prime over V prime, then R is U over V, where V divides V prime. Okay, so we might as well assume that H is base point free. Okay, step 2. So step 2 is just a general situation. So let's say we have some smooth projective variety Y. And let's say we have a bunch of Cartier divisors. And let's say that A is some simple normal crossings divisor with the roundup of A being effective. So another way to say it is that Y comma minus A is KLT. So this is kind of the situation that came up in the non-vanishing theorem, where A was our G. So because this roundup is effective, then that tells you that the coefficients of A are greater than -1, but the coefficients of A are the discrepancies of Y minus A. Then let's define this polynomial PU1 through UK to be the Euler characteristic of the divisor sum of UI DI plus the roundup of A. Again, this is the type of expression that appears in the non-vanishing theorem and also in our commutative type vanishing theorems, depending on what A is. So we'll define this other characteristic, and let's suppose that one, for some UI, this linear combination is Neff, and 2, for the same UI, that this difference between this linear combination and this log canonical divisor for this KLT pair is ample. Then we can apply both commutative vanishing and the non-vanishing theorem under these assumptions. So for these particular UI, we get that the cohomology of any multiple of this UI DI plus the roundup of A is 0. Because this divisor is of the form, is the roundup of a divisor of the form log canonical plus ample. And 2, by the non-vanishing theorem, we have that for some large enough multiples, or for all large enough multiples, this linear series is non-empty. So hi vanish and h0 is non-zero under these assumptions. So this tells us about our polynomial is that P is not identically zero. So it's not just a zero polynomial. But once we know it's not the zero polynomial, it's this polynomial that's of the form Euler characteristic of some linear combination of divisors on Y. And by Riemann-Roch, these type of polynomials have bounded degree. So it's a non-zero polynomial with degree bounded by the dimension of Y. Okay. So we're going to be applying this to produce some polynomial coming from our pair X comma delta. Okay, now why do we care about such polynomials? This is step 3, which is a rationality criterion using these type of polynomials. So let me just write it as a lemma. Suppose you have some numerical polynomial. Which is non-zero. And suppose, well, let's say not zero and of degree less than or equal to n. And now fix some integer a, some real number epsilon greater than 0, and then some other real number with no condition, such that the value of p is 0 for all sufficiently large integers in the following strip. So if we look at this region, ay minus rx is bounded between 0 and our fixed epsilon. And we assume that this polynomial vanishes. Then r is rational with bounded denominator. So the idea then is to apply this lemma to a polynomial p of this form, but where the di's are like the log canonical divisor and the h. And then the a maybe comes from some resolution because maybe we want to resolve everything. So the a is some discrepancy divisor. And because things are KLT, then the a satisfies this roundup condition. And then because of our big NF assumptions, we get that 1 and 2 are satisfied for some x and y. And then we want to be able to apply this polynomial. And this also kind of tells us what do we want to pick for epsilon. Well, we want epsilon to be 1 because that polynomial has degree at most dimension of y plus 1. And what's a going to be? A is going to be the thing that makes kx plus delta Cartier. That's the a in the statement of the theorem. And so ideally what we want to do is just check that the hypotheses of this lemma are satisfied, so that then automatically our Neff threshold R will be rational and we'll get the right bound. The issue is that this isn't necessarily true, so we're gonna have to do a kind of more roundabout contradiction and say, suppose R is not rational, then by this lemma we'll produce infinitely many x and y where this p doesn't vanish, and then we'll use that. But that's exactly, if you think about this p not vanishing, if we're in the conditions 1 and 2 here, then if the polynomial doesn't vanish, then that exactly tells us that, sorry, if we're in condition 1 here, if we have that hi is 0, so if we're in the condition where p and q are bounded or bound R like this, then if we know our polynomial doesn't vanish, that's exactly saying that ph plus q kx plus delta is effective, because in that range the higher cohomologies vanish, so the Euler characteristic is h0. So that's, again, we're going to do all of this carefully, but I want to get some idea of where this comes from. Okay, but we still have to justify why this R even has anything to do with the Neff threshold. Okay, so let A and R be as in the hypothesis of the theorem. So A makes kx plus delta Cartier, and R is the Neff threshold. And now let's define L of P comma Q to be the base locus of these divisors that we're going to work with is pH plus QA kx plus delta. So everywhere we're going to clear denominators on the kx plus delta. Okay, so we can look at these linear series. We can look at their base locus. This might be all of x. That happens if the linear series is just empty. But nevertheless, we have these linear series. So the claim is that if we fix any epsilon greater than 0, and we look at P's and Q in this strip as in our lemma, then for large enough P and Q in this strip, so let me just put it here, for large enough P comma Q satisfying zero is less than AQ minus RP is less than epsilon, then this base locus is independent of P and Q. As a set. Maybe scheme theoretically it could depend, but as a set. And we'll just call it L0. So we'll just define L0. So really L0 kind of depends on these parameters, but we'll define L0 to be this kind of stabilized base locus as you range through all P and Q inside of the strip. And again, this is exactly like how our argument's going to work. Now that we know this base locus is stabilized, then we're going to say Assume R is not rational. Then we have infinitely many P and Q where this polynomial doesn't vanish, that still sit inside of the strip. Therefore, we have infinitely many P and Q where this base locus L0 is stable, but is not all of X, because we're going to have our polynomial doesn't vanish. So we have some sections. And then we're going to perturb things a little bit and apply the base point free argument to lift those sections and cut the base locus even smaller, and then get a contradiction because our base locus is supposed to be stabilized. Okay, so let's prove this claim. And in the process, we'll also set some notation. So I'm going to draw a picture. Let me set my notation xh plus y a kx plus delta. Let's just call this b of xy, some q or even r divisor that depends on x and y. And let's draw a piece of our space of divisors. So let's say this is y, this is x. Then we have some line, the Neff threshold. So this is our line with slope r. Or I guess I put this a over here, so it really has slope r over a. But this is our Neff threshold. And it's cut out by ay minus rx equals 0. So then if we're over here, we're not Neff. So anywhere in this region, bxy is not Neff. If we're on the other side, b is, well, we could say it's Neff, but we actually know a bit more because h is semi-ample and h is big enough. So we actually know that kind of if we're deep enough in this region over here, maybe not everywhere, but there's some open subset in this region where bx comma y is actually semi-ample on that half of the Neff threshold. And so now we're going to look at our some p comma q, some given pq in our strip. So let me draw our strip actually. So our strip is where 0 is less than aq minus rp is less than epsilon. So we're in the region ay minus rx is greater than 0, but then we're bounded by some epsilon. And so we're inside of some strip here. And actually, let me give myself a little more room to draw. Okay, so that's the region that we're working in. And now we have some p comma q in this region. So here's pq. Now we can look at the line spanned by this pq. And now we take some other point. I'm starting to run out of colors. Some other point p prime comma q prime that's large enough in this region. That's not a very good color. Sure. So here's some other point p prime comma q prime. And now the point is that because of these slopes, like we're inside of this strip that has slope the Neff threshold, but then p comma q is outside the Neff threshold. Then kind of if we go far enough up on this PQ line, or maybe not far enough, but if we're at some point on this PQ line, let's call it KP KQ, we can pick, as long as P prime comma Q prime is large enough, is far enough up in this green region, then we can pick it so that this arrow points into the semi-ample direction. And so for large enough p prime q prime, we get that the divisor b of p prime q prime is equal to k times the divisor pq plus something that points into the semi-ample region, so plus something semi-ample. But then what does this tell us? Well, the semi-ample piece doesn't contribute any base locus because, I mean, we can scale it as much as we want and actually make it base point free. And then this k times b piece can only have possibly smaller base locus than bpq, and so that tells us that the base locus of b of p prime q prime has to be contained inside of the base locus of b of pq. And of course, this is all kind of numerical equivalence, but that's okay. So this tells us that the base locus of p prime q prime is contained in the base locus of pq for p prime q prime large enough inside of this region. But now everything's Noetherian, so we have this decreasing chain of closed subsets. The base locus are closed, so eventually it has to stabilize. So there's some set L0, which is the base locus for all large enough P and Q inside of this strip. Okay, and let me just sit on that picture a little bit. Are there any questions about that? And I should say, we actually know a bit more. Not only does the base locus stabilize, it can't be empty. Because a priori we could stabilize to the empty set, but it can't because we're on the other side of the Neff threshold. So these divisors are not Neff, so they can't be base point free. So in fact, it stabilizes to some non-empty subset. Okay. Questions? Okay, so let's just set some notation. So let's set I inside of Z cross Z to be the set of such of these P and Q inside of the strip. And with stabilized base locus. And we're going to set epsilon equals 1 because, like I said, looking at our lemma, we know that epsilon 1 has to be the right epsilon because of this the kind of the bound that we want in the end. But actually, we'll see epsilon equals 1 is exactly what gives us this these pairs where we have q and p and then q minus 1 and p on opposite sides, where when we just subtract 1 from the numerator, we switch sides. Okay, so now step 5. Right. So essentially, now we want to show that this this L0, we show that it's non-empty and that it's the stable base locus well, it's not a stable base locus, but it's the stabilized base locus. We want to show that it's not all of X, because if it's all of X, then there's nothing we can do. There's just no sections. We can't do induction and kind of resolve or anything. So the next two steps are basically dedicated to showing that this L0 can't be all of X. And again, this was going back to our strategy. Saying that it's not all of X is exactly saying that in this strip for large enough P and Q, our divisors are effective. So it's exactly that part of our overall strategy. Okay, so let G from Y to X be some log resolution. I just want to check one thing here. Yeah. So let G be some log resolution, and let's let D1 be the pullback of H, and D2 be the pullback of A kx plus delta. And let A be the discrepancy divisor for this pair in this resolution, so that we have ky is the pullback of kx plus delta plus A. And so now our KLT assumption tells us that the roundup of delta is effective and exceptional. Again, this is kind of the standard facts that come up all the time. And now we can write another way to write this equality is that ky minus A is pulled back from X. Okay, so now let's look at our linear combinations of D1 and D2. These are pulled back, and these are exactly the pullbacks of this BXY that I wrote above. So again, BXY I'm going to use from now on is this notation here. So it's XH plus Y times A KX plus delta. But okay, so D1 and D2 are pulled back. So XD1 plus YD2 are pullbacks of these B's. And so now we look at our polynomial PXY. For this D1, D2, and A. Okay, and so for some X and Y, BXY is big enough because that was our assumption that H is big enough. And when you pull back by a rare rational map, you still get something big enough. And so that tells us that this polynomial is not identically zero, and that it's equal to H0 to global sections in some range by our step two. I think it was step two. Okay, but now on the other hand, this A is effective and exceptional, so we have that the sections on Y of x d1 plus y d2, where x and y are integrals, say, is equal to the sections where we twist up by this roundup of A because this roundup is F exceptional. So it doesn't contribute any sections, and is equal to the sections downstairs, which by definition are the sections of these divisors that we're looking at. Okay, and now, so that was just to say that we can go past to this log resolution, and now we want to show that these divisors are effective in this strip using our assumption. So step 6. So let's just note for a second that x d1 plus y d2 minus ky minus a is pulled back. This is because of this observation that ky minus a is pulled back. So this is the pullback of b minus an extra multiple of kx plus delta. And bxy is when we have y times a many copies of kx plus delta. And so this pullback, when we subtract off one more, it's like the pullback of bx comma y minus 1 over a. Because we're subtracting off, 1 over a many copies of a times kx plus delta. And so again, so this is our point. If we're in this strip, so if 0 is less than ay minus rx is less than 1, if we're inside of this strip of, with 1, then as soon as we subtract off one more copy of kx plus delta, then now we're below the Neff threshold. And so then this is, sorry, it's not an inequality. Then if we're in this strip, then that implies that bx y minus 1 over a, now that we're below the Neff threshold, this divisor is actually big enough. Okay, but if this is big enough, then its pullback is big enough. And so as long as we're inside of this strip, then that tells us that x d1 plus y d2 plus a minus ky is big enough. And so we have the hypotheses of the Kawamoto-Vivek vanishing theorem. So hi on y of x d1 plus y d2 plus the roundup of a is 0. So remember, again, our point is to show that this divisor has sections downstairs on x. To do that, we're pulling back on y so that we can apply like Riemann-Roch and apply our previous part 2. So we need this vanishing, so we know that the Euler characteristic is actually H0. Okay, so now we hit it with our lemma. So suppose, and here we're going to derive our contradiction. So suppose that R is not rational. Then, by our lemma, we have infinitely many P and Q inside of our strip such that the polynomial doesn't vanish on these P and Q because R is not rational. But by our Kawamoto-Vivek vanishing for all these guys in our strip, our higher cohomologies vanish, so this polynomial is actually just equal to the global sections. And so we have that our global sections don't vanish. But again, as we argued before, because this roundup of A is F exceptional, then these are the same as the global sections on X of PH plus QA KX plus delta, or what I called BPQ. And I guess here P is the dimension, so I should put a lowercase h here. Okay, so we've produced sections, assuming that R is not rational. We've produced sections for all P and Q in this strip, and this strip is exactly the strip where we're above the Neff threshold, so our divisor is not Neff, it's not semi-ample, but we're close enough to the Neff threshold so that when we subtract one copy of Kx plus delta, then we're below it, and so everything's big and Neff, base point free, and we're happy. And this is exactly what we said and we wanted to do in our strategy. Questions up to there? Okay, and so we have these effective divisors, so that tells us that this stable base locus is not empty. Sorry, we already know it's not empty. It's not all of X. It's a proper subset because we have some divisors, so it can't be all of X. Okay. And so our point is this is true for all P and Q in I, because remember we defined I to be the subset of integer points inside of the strip that are large enough so that the stable base locus is satisfied. So another way to say it is that for all P and Q in I, we have the base locus is L0 and it's not all of X. Okay, and so now we're going to run our usual base point free argument. So we're going to take a different resolution now. So now we're going to forget about this y. The point of this y was just to prove that H0 is non-empty. Now we're going to take another resolution that's as in the proof of the base point free theorem, where we're going to be able to apply our inductive base point free method to show that there exists some component dominating the base locus of P comma Q, of L of P comma Q, so that when we restrict there, we get sections that we can lift, and therefore that component actually isn't in the base locus, and that'll give us a contradiction because L0 is the base locus for all these P and Q. So we want to pick a log resolution that's adapted to the situation. It's exactly the same as in the proof of the base point free theorem, and even a little simpler than in the proof of the non-vanishing theorem. So let f from y to x be a log resolution such that our usual properties. One, let's just write down the discrepancies. Ky is the pullback of kx plus delta plus our discrepancy divisor, which we'll write down as sum of bj fj. Sum of aj fj for aj greater than -1. Two, we'll pick things so that we can perturb by some exceptionals to make the divisor of interest ample. So let's assume that the pullback of pH plus QA minus 1 KX plus delta. Remember, this is another word for BP Q minus 1 over A. So here we're below the Neff threshold. So this B is big enough. Because this B is big enough, then we can pick our resolution so that the pullback perturbed by some exceptionals is actually ample. This is the argument that appeared in the base point free theorem, and again we can do this because this is big enough. And finally, let's suppose that we've resolved so that our linear series, which is now that it's effective, so here's where we're using that our linear series is effective. So let's assume we've resolved so that our linear series is something base point free plus something fixed. So now this is our divisor right above the Neff threshold. So let's say that this is L plus the sum of Rj, Fj, where L is base point free, and these are fixed. And let's assume that everything inside is simple normal crossings. So we've resolved enough so that all the f's are smooth. They intersect transversely. They intersect transversely with L. Everything's nice. Okay, so this is exactly like in the base point free theorem, just with these divisors BPQ and BPQ minus 1 over A instead of whatever our fixed divisor in the base point free theorem was. Okay, and now we're gonna run the same argument like before. So I'll just kind of summarize what's gonna happen. So just like before, we'll define some expressions of the form minus C Rj plus Aj minus Pj. This is exactly the same expression that came up in the previous two proofs. And we'll pick the C and our perturbations Pj such that this can be written as A prime minus F, where F is integral. So it's a reduced divisor with coefficient exactly minus 1. So we'll pick C. So we'll pick the C and the PJ. So there's a unique component with coefficient minus 1 in the sum. Because the coefficient is negative, because the coefficient is minus 1, then we actually need F to be one of the divisors with Rj greater than 0. That's the only way that this type of expression will ever have coefficient exactly minus 1. So that tells us that not only is it integral and reduced, but it has to be part of the fixed locus of the pullback of this linear series. So of the pullback of B of PQ, because it has to be one of the divisors with R greater than 0. And then moreover, everything else, this is the smallest coefficient, so everything else is A prime, has coefficient bigger than minus 1, and so the roundup of A prime is effective. And again, if we look at the coefficients, when is the roundup not 0? It's exactly when you have coefficients strictly bigger. When you have coefficients strictly bigger than 0 before you round up, and so whatever's left over, not only is it effective, but it's actually exceptional as well. So everything non-exceptional has some strictly less than 0 coefficient, so it becomes 0 when you round up. Again, this is exactly like in the proof last week. And then we'll write down the same type of linear combination for n. So now C is fixed. These PJs are all fixed. We've picked them so that all these properties are true. But now we have P and Q that are varying. So we'll write down an n in terms now of some P prime and Q prime, which are related to P and Q, and we'll see in a second what they need to be so that this n is ample. Because remember, in our base point free method, we need n to be ample so that we can restrict and induct. So this n will be F upper star B P prime Q prime plus this A prime minus F minus KY, just like before. And now if we write all of this out and kind of expand everything in terms of this sum of the F's and these pieces here where the expression in 2 is ample and this L is base point free. So we write everything in terms of this ample and this base point free. Then we'll see that that this is ample exactly when P prime and Q prime are large enough and they're not in the same strip as P and Q. So we fixed some P and Q and I, but now we're looking at an even smaller strip. So P and Q are in this strip of width 1, and these P prime and Q prime have to be large enough numbers inside the strip so they're inside the strip defined by this by the value for Q and P. Okay, and that's just a computation. Like you expand out this n the same way we did before, and just see that you need to be exactly here so that you're like ample minus just so that you're like ample minus big enough. Okay, so I'll leave you to expand that out. But now that we have this set up from our base point free method, then we have surjectivity of the map on sections for this P prime and Q prime. So we have surjectivity when we restrict onto this F. Just like before. Again, because we've written our n as our ample is the divisor plus an A prime that we want surjectivity for minus this ky plus f divisor where we have a junction, and so we get commutative vanishing, and because n is ample, and so we get the surjectivity. And now we check, well, n restricted to f is ample, but from its expression, this is the pullback of P prime Q prime plus A prime minus F minus KY restricted to F. And so by junction, this is this thing that we're surjecting onto. Minus KF. And so this divisor satisfies, so this divisor is, so yeah, this divisor satisfies all our hypotheses because it's of the form KF plus ample. And so by step two is this statement about when you have a polynomial of the form Euler characteristic of linear combination of divisors plus a roundup. So our linear combination is exactly here. This is the pullback of a P prime Q prime linear combination, and so we just apply our lemma to D1 and D2 being the pullbacks of those divisors. A prime is just like in our polynomial statement. So this tells us that the polynomial on F given by the Euler characteristic of the pullback of B P prime Q prime plus the roundup of A prime is not identically 0 because we have some value where when you subtract KF, it's actually ample. And we have that the cohomology vanishes for this P prime Q prime on F because it's KF plus an ample. So there's our induction. And so what do we know? Well, then we know because it's a non-zero polynomial and we know that the HIs vanish, then we know that by step 3, for all p prime, q prime in the strip, so in the smaller strip now whatever we are aq minus rp, this will be epsilon in our inductive application of the lemma. So by that lemma, for all p prime and q prime in the strip, we know that, for all large enough, there are infinitely many, because we're trying to do a contradiction. So the lemma says that if you have something for all large enough ones, then R is rational. Because we assumed R was not rational, then we know that there are infinitely many p prime, q prime in this region that are large enough and that satisfy that pf of p prime and q prime is not zero. But by this work above, because the cohomology vanishes, then this is actually the global sections. So those global sections are not zero if we assume that R is not rational. And now I know we're out of time, but there's one more. Now we're basically there. So now by surjectivity, so if we go all the way back here, we have this surjective morphism I'll call star star, and we've just checked that this is not zero in step 9. So now by surjectivity of star star, then we get that h0 on y of p prime h plus, the pullbacks of these. So of the pullback of b p prime q prime plus the roundup of a prime not only is not zero, but it has a section that doesn't vanish identically on f because it's pulled back from some non-zero section of the restriction to f. So it has this section such that s restricted to f is not identically zero. But that tells us that f is not in the base locus. Because again, here we're twisting by something effective exceptional. So this is h0 on x of this b p prime q prime. So because when we pull back, we have a section that doesn't vanish on f, then downstairs on x, we have a section that doesn't vanish on f of f. So that means that f of f is not in the base locus of p prime q prime. But this was true for all p prime and q, for infinitely many p prime and q prime large enough. And this is supposed to be like our stable. So this contradicts the fact that we actually stabilize, because then this tells us that this is a proper subset of L PQ, which was our stable L0, and so that gives us a contradiction. Because we said that for all large enough P and Q, our base locus is supposed to be the same, but now we found this sequence of P prime and Q prime that are still in our strip because they're actually in a smaller strip, where for those P prime and Q prime, we can cut down the base locus even smaller. Okay, so that gives us a contradiction. So R is rational. And now the unfortunate part is to get the bound in the denominator, we actually need to run through the whole argument again. Thankfully, it's almost verbatim. But the issue is that now that R is rational, we want to just apply this lemma and just say, well, look, the bound in our lemma is exactly the bound we want in the denominator. The issue is we don't actually have the hypotheses of our lemma. what we did was, like, we didn't prove the hypotheses of our lemma are true. What we showed was if you assume that R is not rational, then the hypotheses are not true, and that gives you a contradiction. So if you could prove directly that the hypotheses of this lemma are true, then you're good, but you can't do that. So now we basically say, okay, R is rational, but suppose its denominator is not in this range. Then again, the hypotheses of our lemma can't hold, and then we run through the same type of argument, derive a contradiction, and get the right bounds on the denominator.